Hey, good morning, everybody. Thanks for joining with us today. I think we've got a good amount of attendees so far, so we'll go ahead and get things started here. Okay. Well, first of all, thank you all for joining today. We've got a really exciting presentation today. My name is Chance Borger. I'm the Technical Sales Director here at OGI, and the presentation today will be put on by our R&D engineer, Jim Benzo. So really excited to get into the thermostatic versus intermittent pilots and some of the details with that. So with that, we'll go ahead and get started. I'll first start with a little bit about OGI if you are not familiar with our company. So we specialize in everything oil, gas, and industrial. Our product that we'll be talking about directly related to today is the Terry brand water bath heater and the pilots that go along with that. We do also have the quick water, which is more into the industrial area, but it's a direct contact water heater. But our main thing is we specialize in all things heater. Some of the industries that we're in are the natural gas, food, beverage, and then with the quick water side, we get a little bit more into some of the pharmaceuticals, car washes, different manufacturing industries, and government agencies. And we are also very proud to be a women-owned business, and happy to be a part of that organization. Finally, we've been in business for about 31 years, coming up on 32. So have a lot of experience, especially Jim has a ton of experience, and he's going to talk to you all a little bit more about that today, and some of the things that we're doing. So with that, I'm going to hand it over to Jim, and we will get started.
Hello, everybody. Welcome to basically pilot options and thermostatic versus intermittent pilots. I think as an outline you can see already, we're going to talk about the heat release under normal conditions that promote the use of alternate pilots, the heat release associated with standby operation of a heater, and then we're going to dive into the pilot options itself. First of all, we need to understand kind of the flow of energy that's going to flow through a heater and under normal conditions. And reviewing this typical energy balance, we see that the usable energy that we have available is actually what we're focusing on. And this is under normal conditions when the main burner is operating and really producing the energy that we need. So as a result of that, the usable energy that we get out of the heater that we're focusing on is about 65 to 77%, depending on what we actually have for an efficiency and overall efficiency in a natural draft design. The gross heating value associated with that is relative to the hot exhaust gases that actually take away from those losses, as well as the loss through the heater shell. So we have a gross heating value that's actually put into the heater, and then as a result, we also then receive energy from the heat transfer that's going to the natural gas that's flowing through the process coil, and then we have losses that are going up to the stack and through the shell. Under typical heater control designs, we typically want to design this based on the maximum duty. You know, what's our flow rate? What's the pressure drop that we're looking to take across the regulator downstream, and things of that nature. So right now we're kind of building a foundation of the true design of the heater based on the overall duty that we're trying to satisfy. And then we typically design the heater based on its intended operation. Is it for a border station to take account for the pressure drop through a station, or is it used for fuel gas where we're driving the gas temperature up to avoid elemental sulfur formation? And then we also are interested in the operating periods. Is it a seasonal operation through the shoulder months, through the winter, and then And then, basically September through April, or is it year round? These are things that obviously also play into the design under a normal operation. At this point, though, in standby, it says, what happens when the burner is not operating? The focus turns to the pilot impact on the heater operation. And then it's like, what must we consider choosing between when choosing between pilot operating options? So to do that, let's look at that same energy balance that we had earlier but in this case, let's look at it relative to the pilot operation. So first of all, we actually have still a pilot input. We have energy input that in this case, so instead of it being based on the total rated duty of the heater, it's only relative to the pilot's input. But in most cases, it's about 11,000 BTUs per hour net input. Now, that varies obviously with the type of pilot. So again, decisions on the type of pilot are important as well. Then, of course, we still have process flow. Well, in most cases, we have process flow, but there are also cases where, like for a fuel gas heater in standby operation, there may not be any process flow. So the amount of energy that's being pulled from that heater water bath is fairly small relative to the overall design of the heater. As far as the stack is concerned, previously we had a significant amount of energy that was going up the stack. Up to potentially 33% of the heater's capacity was literally exhausted up the stack. In this case, though, because we're talking about a pilot operation that's only pulling in about as much air as necessary to maintain its air supply, the stack temperature will actually fall to approximately the water bath plus enough draft to promote or to support the stack. Now, my scenarios are primarily driven towards those that are going to be during the off-peak periods of time, which in that case would be between April and September. In the wintertime, the draft will be a little bit higher, but when just the pilot's running, but not anywhere close to when the main burner's running. But the most consistent loss that we have through the heater is actually through the shell. It remains fairly consistent to normal operation, but it's primarily affected by is relative to the insulation, the thickness of the insulation, the type of insulation, the ambient temperature, the wind, and the weather. So essentially, the more still the air is, the drier the climate, the higher the temperature, the less the losses are through the shell. So in this case, what we understand now is through evaluating the losses that we have through the heater, we must consider the natural gas minimum flow rate, the ambient temperature, and the bath volume. So these are all things that actually will impact the ability for the pilot to be able to be maintained on a standing basis or a continuous basis, or do we need to seek alternate conditions or alternate pilot options? So what we'd like to do is take a look at evaluating that standby condition. To do that, we're gonna make some assumptions. The first thing is that we're going to take an assumptions associated to the heater. We're going to start with a bath temperature that's about 60 degrees. We're going to assume we're using a continuous 11,000 BTU pilot. We're going to use a consistent 2-inch fiberglass insulation on the main shell, but the end plates won't be insulated, which is a typical heater design. Obviously, if your heater has insulation on the ends, it'll actually change some things a little bit, but we're going to assume that they're not insulated. And then we're going to also assume that the bath media is a 50-50 ethylene glycol water concentration. And then we're going to make some ambient air or conditions associated to the environment that the heater's installed. So we're going to assume this is a summertime operation because that's when the lowest natural gas flow rate is typically seen. Through a heater, or in case of a fuel gas heater, it'd be obviously zero. The average ambient temperature, and this is an average, so that means your high and your low are going to basically straddle this 70-degree ambient temperature number, because obviously this heater is going to be exposed to evening and full sun application. So 70 degrees is a good kind of middle of the road number. Wind speeds, there's two different wind speeds that we evaluated, and one of them is very calm, 5 miles per hour or lower, and then what's considered an ASHRAE standard for design, which is 15 miles per hour. So we're looking at both of those. In doing so, what we found is that, as you can see in the attached table, this summarizes this analytical review of the effect of warm ambient, low natural gas flow operations on small heaters, ranging from a Terry 125 to a Terry 750. Our goal was to better understand how long a small bath could operate without over-temping the bath, i.e. causing the heater's control system to shut down on high bath temperature, typically set in most cases for OGI's Terry brand at about 190 degrees Fahrenheit. The minimum flow limits column presents the predicted natural gas turn down where the heaters being evaluated are subject to the minimum natural gas flow rate that would allow the heater, or just below that would allow the heater to overtemp. In this case, most of them that you can see, like for the Terry 125, the minimum flow rate associated with that heater would be about a 20-to-1 turn down, and that 20-to-1 would actually cause for an overheat condition in either the 5 mile per hour or the 15 mile per hour range. But if you go to the Terry 750, you actually see in that column that you could almost flow 200-to-1, and if you flowed slightly less than 200-to-1, let's say you flowed 150 or even 100-to-1 on that larger heater, you would have enough energy flow through that heater to make up for the energy input of the pilot under a standing pilot or continuous pilot operation. On the no flow situation, this basically is saying I'm not going to allow any flow of natural gas through the heater, even naturally. There's for a fuel gas application, if a turbine downstream or a user downstream is completely offline, you'll have a static operation of the heater where basically the heater is going to have to survive on its own without any type of additional control. In this case, you can see that the 125, the Terry 125, which is a 20-inch OD heater, can barely last a day, if even that long. Again, this is starting at 60 degrees Fahrenheit, and on a fairly warm day with either 15 or 5 mile per hour winds, while the Terry 750 can last up to 4.5 days in a 15 mile an hour wind. Now, all of these kind of show a relative trend, right? So if you look at the 125, there's only 90 gallons of volume, of water volume or thermal capacity to absorb the energy that is being driven by the pilot. And of course, the surface area on the outside is limited by the length and the diameter. While we go to the Terry 750, and now we're actually seeing that we have about 575 to 600 gallons of thermal mass available to absorb the energy, and a larger surface area on the outside to allow more energy to be just naturally conductively released to the ambient to the atmosphere. So I guess in this case, what have we learned? What heaters are most impacted by a continuous pilot operation? The first one we talked about was fuel gas heaters during standby periods when no fuel gas flow is actually flowing through the heater. More effective. This is more impacted during warmer weather. Summer operations when the heater's just in standby mode. Winter operations, it's still likely but less likely because there's enough differential in temperature between the ambient and the bath to avoid that situation. The other thing is smaller heaters during off-peak season periods, and sometimes even during normal operation. It all depends on the size of the heater and the location. But obviously, when ambient temperatures are high or warm, and natural gas flow rates are very, very low. So what options do we have? Well, the options that are available to avoid a continuous pilot operation or an overheating of the heater are twofold, really. A continuous pilot with thermostatic control. In this case, the pilot is consistent with the current standing pilot philosophy, where the pilot is always lit, but it has its own temperature controller that will actually allow the bath temperature to warm to just below that shutdown condition that would lock out the heater, and it'll shut off the heater or the pilot and then allow the bath to cool and then relight the pilot again. So it actually operates on its own. If you could consider, it operates on its own individual call for heat that's specific to the pilot. The other alternative is the intermittent pilot. The intermittent pilot has the ability to actually operate the pilot and the main together. So when there's a main burner call for heat, the intermittent pilot will be, or the pilot will be lit first and proven, and then the main will be lit. This is more traditional to what you would see like in a forced draft heater, where the burner will purge, light the pilot, and then light the main. And then in this case, though, the pilot will remain lit during the duration of the main burner operation. What I'd like to do is talk a little bit about the advantages and disadvantages of each of these. So for a continuous pilot with thermostatic control, the advantage is obviously the pilot remains lit, eliminating the pre-purge requirement between main burner operations or cycling. It also ensures that the heater readiness is ready for operation for the main burner. And this is one of the reasons we all know in the industry that the heart of our heaters is the pilot and the integrity of that pilot. So making sure that it's lit at any time is always one of those situations that, from an advantage standpoint, that outweighs any other option, is to find a way to maintain that pilot operation as long as you possibly can. The disadvantage is obviously to maintain that pilot operation as long as possible, you actually will develop a warmer bath during these shoulder or non-shoulder, but the off-season or off-peak periods during the summertime. So that is a definite disadvantage, and obviously you'll be burning gas the whole time. The alternative to that is, in some cases, some of our clients, they literally just, in those off-season periods, they literally just shut off the pilot and let the heater just sit, and that's not an uncommon practice. The intermittent pilot advantages, the pilot operates with the main burner call for heat. Obviously, we discussed that earlier, but it minimizes heat input, just as and only to when you actually need the main burner to run. It also reduces your natural gas usage. That goes without saying. The biggest disadvantage, though, is that it does require a 5-minute pre-purge period between each pilot operation. So if you're in a cycle period where you satisfy during, let's say, a shoulder month operation, where maybe that burner has to kick on and off in less than 5 minutes to keep up with your capacity, it will actually fall behind in operation if it's not able to keep up, which is going to cause you to have to adjust some control set points higher to kind of provide you some grace in your control. For the TotalArc BMS, we have that available in multiple configurations. Right out of the box, the BMS is actually available in a thermostatic thermostatic pilot configuration. Hold on. Sorry, guys, I'm just checking my slide here. So for a pneumatic configuration, under a thermostatic pilot, in this case, we'll actually be using a single switch. So this out of the box, a standard BMS that's pneumatic will have a single pressure switch, and that's going to monitor the low water level and the high bath temperature pneumatic conditions. That all by itself is going to give us some feedback, and basically with that, this PS 100 connection is actually connected directly to the BMS call for heat input, which, as a result of that input on a thermostatic pilot, will automatically open the SV, the pilot valve, and improve the pilot. And then after the pilot is proven, it'll enable the main burner solenoid valve. Now, because the solenoid valve is enabled, doesn't mean that it's actually going to operate the main burner. The main burner will operate based on the process temperature controller that's located downstream of SV 101. So essentially, every time there's a call for heat, the thermostat, the BMS will light the pilot, and once it's proven, it'll open the solenoid valve 101 and wait, and the main burner will have to wait for the call for heat to be driven by the pneumatic controller. In an intermittent configuration, the BMS, we would relocate the pressure switch to be just downstream of that process temperature controller, and the input would still be driven into the BMS call for heat input. But one thing that's interesting about this is that not only are we monitoring in that call for heat input the TC109 feature, but we're also including the pneumatic signals from the low water level and the high bath temperature. So all of those are gathered together in the same input. From there, again, it's going to scroll through the same process, but in this case, instead of the main burner having to wait for the pneumatic controller to be enabled, all it's going to look for is that the pilot is proven, and once the pilot is proven, then it'll directly light the main burner. And then, of course, when that call for heat or when that pneumatic controller says I'm satisfied, both the pilot and the main will be shut off. In the case of a BMS, a pneumatic BMS with lockout, this is a little bit more complex, but very doable control system. This actually will take and monitor the safeties directly by taking PS 100, which is monitoring the bath and the bath temperature and the bath level, and putting that into a heater safeties input. And then it's taking the PS 101, which is a new pressure switch or an additional pressure switch, and monitoring a bath temperature controller. Now, with that, it's going to require the addition of a second bath temperature controller over what a standard heater would require. And again, this is a thermostatic pilot control. So once that is satisfied, that's going to be tied into the BMS input, which is going to light the pilot. And then again, just as it did before, it's going to then look for the pneumatic control for TC109 to drive or enable the main burner to operate. realizing again that SV101 is directly tied to the condition of the pilot and of course the heater safeties and the BMS call for heat input. So finally, in the pneumatic version, we have the intermittent pilot. In this case, again, it's of a similar configuration. We're still monitoring the safety conditions, the heater safety conditions through PS100. That's going directly into the heater safeties input. We're going to monitor the process condition. In this case, instead of it being upstream of the TC109, it's going to be downstream of TC109. The one would say, well, what's the difference here between the first version and this one? Well, the primary thing is that the bath temperature, in some cases, some of our clients who require or request a second bath temperature controller that is well below, in this case, you can see it's approximately 30 degrees below the high bath temperature shutdown. This way, the process temperature and the bath temperature are both influencing the operation of the burner, and in this case, the pilot. So in this case, the pilot, again, the PS101 is driving an input into the BMS call for heat. We have, from there, we have a solenoid valve that is going to open prove the pilot. Once the pilot's proven, the main will be lit. And you can see here again that the pilot and the main control are driven by both of those controllers. In the case of an electronic BMS, the heater safeties are directly being monitored by a high temperature electronic switch that's monitoring a type K thermocouple that's located in the bath, and of course an electronic low water level switch. Both of those are voting in and giving a heater safety input into the BMS that says, okay, hey, it's safe to operate. The BMS call for heat is actually being monitored, or is monitoring both a normal bath temperature control set point that we're looking for, as well as a process temperature set point. Now, this is kind of an and/or situation. Again, if we look back on what some clients prefer, they just simply want a bath temperature control. Some just want a process temperature control. In the process temperature control, we've seen typically there's two alternatives. As you can see here, we have either alternative one where the temperature control monitoring point is located in the outlet of the heater, or alternative two where it's located downstream of a client's regulator. The most common, obviously, for reg stations is that they want to know and they want to protect and ensure that that temperature downstream of the regulating point is meeting the minimum requirement that they have associated with their delivery. For our application today, we're just going to continue to focus on the alternative two to kind of round out how this system is going to work. So as far as the intermittent pilot, essentially the BMS system right out of the box is set up electronically as a intermittent pilot control. Again, the variation on the temperature switches and the temperature control points is all based on customer need and whatever they define. But right now, what we see is that with that being out of the box, we have a thermostatic jumper that would actually be installed in place of an alternate control. From that, we'll see that once, again, based on the temperature input from the BMS call for heat, once that is satisfied, as well as proving the safeties are okay, the pilot will be lit, and then the main will follow once proven. So the operation is just like it was on the pneumatics, but in this case, it's fully electronic, and the variation in the gas trains are minimal. On the thermostatic side, again, we've got the heater safeties is the same. It basically is monitoring the high bath temperature here, as well as the low water level. In this case, though, with thermostatic pilot, the BMS call for heat is simply monitoring a temperature that will be actually controlling the pilot, while the main burner will be actually controlled by the process condition and or the controlling bath temperature. Again, it's all based on customer requirements. For this thermostatic operation, the thermostatic jumper will be removed and will allow the burner to run independent of the pilot, and then the pilot itself will be cycled off when it loses its call for heat that's independent again of the main burner. So here again, I'm just illustrating that the responsibilities of each of these two inputs, because the jumper is removed, is now independent of each other. So the process conditions are being satisfied by the main burner operation, while the heater is being bath is essentially being protected by the thermostatic pilot. Well, that's all I've got. If there are any questions, please let us know.
Yeah, looks like we've maybe got a few questions here. Okay, well, these are just about the presentation. So yeah, Stacy addressed that. So yeah, we'll be sure to share the presentation with all of you after this is over. But I'll give you all just a few more minutes to ask any questions you have, and then after that, we'll go ahead and finish this up. So just give you guys a minute or so here to ask any questions you might have. Okay, well, I think that's probably also, I mean, Seth maybe has a question here. Give him a second. Okay, so yeah, Seth asked any provisions for control to call out when the heater's down, I think is maybe.
Yeah, in the case of either the pneumatic or the electronic, there's a remote or a trouble contact that's available. The heater configuration would be, in the event if it's set up as we've shown in the pneumatics, where the call for heat is being monitored by the heater safeties, it would give you a call out if the pilot, for example, failed to relight. There's other configurations that basically says if I lose a heater safety, and that's for either electronic or pneumatic, that call out or that contact, a trouble contact, would be enabled or energized in the event that a trouble was occurring. So you'd get remote indication of a problem.
Okay. All right. Just maybe a couple more seconds for any more questions, and then we'll wrap things up. Okay. Well, thank you all again for joining us, and thanks to Jim for putting on this presentation. And like I said, we'll email this out, and you'll have all of our contact information. So if you think of anything after this, feel free to reach out. We'd be happy to answer any more questions. So thank you all again, and have a good day.